In this video, we're going to take a look at some of the properties of matrix multiplication. But I'd like to start by reminding you what some of the properties of matrix operations we already know. These are the properties of matrix addition and matrix scalar multiplication. We can add two matrices together, and it doesn't matter what order they're in when you add them, you get the same result. You can add two matrices together and add a third, or you can add the second and third matrix together and then add that result to the first matrix. As long as the three matrices are the same three matrices, you can associate different matrices when you do the addition and you get the same result. You can scale a matrix first and then scale it again, or you can multiply the scalars and then scale the matrix by that entire scalar all at once, and you get the same result. You can sum two matrices first and then scale the resulting matrix, or you can scale individually the matrices by the same scalar and add them together and you get the same result. And if you add the zero matrix to any matrix, you get the same matrix back. So those are the properties that we learned when we were just learning about matrix addition and scalar multiplication. And now we're going to talk about the properties of matrix multiplication. Each of the properties for matrix multiplication can be associated with a property for matrix addition or scalar multiplication. So I'm going to try to line these up. I'm going to skip the first one, which I hope it'll be clear why I'm doing that, but I'll come back to it and explain, what that property is, how it relates, and why that one's different. So the first property I want to talk about, though, is that if you have three matrices, and for matrix multiplication, they just need to be the appropriate size, right? They may actually be different sizes. With addition, we had to have the same size, appropriate for multiplication. And for addition, they had to be the same size. Okay, so the first one we're going to talk about is this second property here. And that is that it doesn't matter which two matrices you multiply together first. When you multiply them by the third, as long as you're working with the same three matrices, you'll get the same result. So in other words, I can multiply the matrices B and C together first, and then multiply the result by matrix A, or I can multiply A and B together first, and then multiply the result by matrix C, and I'll get the same answer. I'll get the same matrix. That's called the associative property of matrix multiplication, where this property here was called the associative property of matrix addition. That's why I wanted those on the same line. Our next property says that we can multiply two matrices together, A and B, and then multiply the resulting matrix by some scalar. Or we can multiply one of the matrices by the scalar and then multiply the resulting matrix by the other matrix. Or we can even multiply the second matrix by the scalar and multiply the result by the other matrix. And whichever order you do this, or wherever you place the scalar, you'll end up with the same result. Right? So my scalar is in the front here. It's outside matrix multiplication first and then scale the whole thing. This one's just scale the matrix A, then multiply the resulting matrix by B. And this one says scale the matrix B first and then multiply A by the resulting matrix. Notice that in both cases here, this associative property and this associative property of scalar multiplication, both of these require that A is on the left and B is on the right, or A is on the left, B is on the right, A is on the left, B is on the right, and C is on the right of B. If we change the order of the matrices, we run into the problem that we did in the last video, sorry, 2 videos ago, where we have matrix multiplication, which is not commutative. I cannot just multiply two matrices together in any order and expect to get the same result. That's true in the real numbers, but it's not true for matrices. So while I'm saying that it doesn't matter where the scalar is, it very much matters what order the matrices are in here. Same thing with this one. Okay, the next property we're going to talk about is one called the distributive property. And that says that I can take two matrices, I'm going to say B and C, and add them together. And I can multiply the result of that. That's going to be a new matrix. I can multiply A by that new result. Or I can take A and multiply it by B first, and then A and multiply it by C, and add those two together, and I'll get the same thing. Okay, that's the left distributive property, but we also have a right distributive property, which is important to note because matrix multiplication is not commutative. So let's gonna call this BA plus, I'm out of room here, plus CA. Because matrix multiplication is not commutative. So I have to distinguish between the fact that here I'm multiplying the sum of two matrices by another matrix. I'm actually multiplying the matrix A by the sum. Here I'm multiplying the sum by a matrix, and those are different because matrix multiplication is not commutative. So I have the left and right distributive properties of matrix multiplication. Then I have the identity property, which says that if I take the identity property, the identity matrix M, and multiply it by A, assuming that M is the square matrix appropriate for that multiplication, or I take the matrix A and multiply it by the identity matrix, it may have a different dimension. Either of those are going to be the same, and what the result is A. So this is the multiplicative identity for matrix multiplication, where this was the additive identity property for matrix addition, the identity property for matrix addition. Okay, now I'm going to do the last one, which was actually the first one on the list. And that says that it doesn't matter what order you multiply matrices in, you get the same result. But that is not true. Where we have a commutative property for matrix addition, we do not have a commutative property for matrix multiplication. So I've used the closest thing this palette has to a red to indicate that this is not correct, but I've also used the not equal symbol. If you're using note cards or some kind of mnemonic device, be sure to copy down this little factoid. It's nice to have a list of properties, but this is such an important, it's not really a factoid, it's a really important piece of information. It's worth its own bullet point, but it's also worth being very, very clear that this one is not true. The order you multiply two matrices together in is very important. It does make a difference, and they very likely be different. The results will be different. Because I'm trying to provide at least some proofs in this class so that you get used to seeing them and knowing what some proofs maybe look like, I'm going to prove one of these properties. Your textbook does a proof of, it calls it property 4, which is the associative property of scalars in matrix multiplication. And that is, which one was that? That is, that's this one right here. Oops. That is this property right here. And it does that by using this sigma notation and the fact that the entries in a matrix are real numbers, and it applies the properties of real numbers to do that. I'm going to prove that the order of multiplication of matrices is important. That is, I'm going to prove this statement here, that AB is not equal to BA. And I'm going to do that by something called a counterexample. It's actually a lot easier to prove that something is not true if you can find what's called a counterexample. All a counterexample really is an example of the statement. For example, if this was AB equals BA, I could prove that this was not true by showing an example that demonstrates that, right? So I give an example of an AB and a BA, which when you multiply them together are not equal. So that's what I'm going to do here. I'm going to start by establishing the two matrices that I'm going to work with, and then I'm going to multiply AB, and then I'll multiply BA, and I'll show that they're different. All right, row 1 times column 1 is 0 times 2 plus 1 times 1 is 1. Then I have 0 times 1 plus 1 times 0 is 0. And I'm ready to do row 2. 1 times 2 plus 1 times 1 is 3. And 1 times 1 plus 1 times 0 is 1. So that's the result of multiplying A times B. All right, now we're ready to do this multiplication in the opposite order. So we have 2 times 0 plus 1 times 1 is 1. 2 times 1 plus 1 times 1 is 3. And already I can see that they're different. So I could just finish, but because I'm doing a proof, this is a little bit more formal, I'm going to go ahead and see this out. 1 times 0 plus 0 times 1 is 0. And 1 times 1 plus 0 times 1 is 1. Now they're very similar. They have all the same numbers. And in fact, the only real difference is the order in which the 3 and the 0 appear in the two matrices. But that's enough to call them different. So I'm going to say that since AB is not equal to BA, it cannot be said, it's not true that AB equals BA for all matrices. Right? If I just take any matrix A and any matrix B and multiply them together, if I do so in the opposite orders, there may be a time, in fact, it happens most of the time, but if I can only find one, that's enough to say that this statement that AB equals BA is not true. So I have proved that AB is not equal to BA simply by showing one case where the two products are different.